we can do some numerical examples with different size. We can see the first merit function have this behavior, which can compute, which computed different numbers of experiments, the m number experiments, which are scaled with the number with the size of the system. There is a crossover here, so for a large number of networks, we have the number of experiment needed for a perfect performance is determined by this crossover.
Right.
Yes.
So when you mean experiment, you run, so you don't have any noise.
Any noise?
No noise.
No noise.
So it's a linear model in which you sample the X many times,
yes,
many Ys, and then you try to recover.
Yes.
So you're okay. So you're doing matrix factorization, and you're trying to. So like if every experiment you put it in a row, then you have every Y in a row, then you have this matrix has to be equal to this matrix times this matrix. You're trying to understand which is the A matrix.
Yes.
You're doing matrix factorization.
Yes. Looking for the sign of the connectivity matrix. So we can see also that the behavior of information gain as increased alpha parameter. So this is a behavior that complements this one almost. So there is saturation with we have a perfect performance. In this case, I will use a priori probabilities are equal for this case. We can see also that for n equals 60, we can see that this corresponds for that for the case of incomplete information, for example, in this case, there is some regulatory links that are accurately inferred, but we don't know which are. For example, if we consider this plot is showing the connectivity matrix, where only 5% of the entries of the matrix entries are different from 0. This corresponds with the gray background, and we try to reconstruct with only 24 experiments. That is with incomplete information using the IT approach. So we can see that there is these green circles. This is the predicted sign of the weight. We can see the green circles are well predicted links, but there are also some wrong predicted, which are over two, mainly over two regulated genes in these lines. Okay. So this grouping is related to the set of experiments used to infer the links. Other set of experiments have different genes. Looking at this picture, I have two questions. One is how to select the set of experiments for a specific outcome, and the other is how to select the predicted links correctly. The approach, the ATAP approach, can also provide a score. This score is the a posteriori probability. For example, the green circles are indicating the links predicted with the probability a posteriori, a posteriori probability with a high greater than 0.99, and almost of them, except one, are correct. So we can use the a posteriori probability as a score to rank the predictions. For the question 1, I will make another example, numerical example, considering that biological networks are organized in communities. These communities are weakly connected. So my question is how to select the best set of experiments to reconstruct one specific subnetwork completely. In this case, this is the subnetwork. This consists on a subnetwork with 10 nodes, which is embedded in a more complex network with 100 nodes. So in the first case, I will construct one experiment where gene 1 is overexpressed. Gene 1 is I know that it belongs to the subnetwork, and I can compute the information gain related to this experiment, and we can see that this information gain is concentrated around gene 6. So I can infer that gene 1 regulates gene 6, but I don't know how. So I can repeat the experiment overexpressing gene 6, and again we compute the information gain, and we can see that genes 2 and gene 3 the information gain is concentrated here, and we can conclude that these genes are regulated. And we can do again for all genes that appear in this list until no new genes appears. Oops. So we can use this list as an a priori information to set in these a priori probabilities. For example, if gene 1 regulates gene 6, I can assume that this probability a priori is 0, and the others are equal. If we do for all lists, and we put ones for the a priori probability for all other cases, and use all previous experiments at once and repeat the IT approach, we can recover completely the subnetwork. So the IT approach can be used to infer interactions. It offers also scores to rank the predictions. Also, the method can handle with a priori information, because I can set the a priori probabilities and use previous information. The method can also deal with the sparse networks, and we illustrate an example on how to design the experiment sets the set of experiments to reconstruct a specific networks. As perspective, this approach has lower performance when we have noise. When use the sparse prescription I show. So we are working with how to improve this. We are also working with how to work with few experiments at the steady state, and also phenotypic transitions. Thanks for the organizers and Infernet, ICTP for the financial support.
There is any question? I do have one. Do you have a size limitation for the network size? Or smaller, no can be smaller than in size, or bigger than?
I see the size, depends on the size of the computers.
Oh, okay. It's a good point.
But maybe the question is how does the algorithm scale with the size of the network?
It's the same. The performance is the same when I scale with the performance with the size. The curve is almost all equal.
No, but the computational load, how does it scale with the size of the network? So if I start with a network of 10, Okay.
I didn't do it, this computation. How is the performance of the method with the size in the time, in terms of time?
The computational.
Computational
takes
time,
a lot
yeah.
from-
It's quadratic.
Yes, I don't know.
Okay.
Any question? Okay, let's think, please, again.